Hello, everyone. Welcome to the virtual Best Paper Award session. And let me share my screen to show also the golden certificate here. So can you see that?
Yes, we can.
Okay, excellent. Thanks for the feedback. All right, so because we're running a bit over time, I don't want to spend too much time for it. First of all, congratulations to the team of David Keyes, and I think Tariq and Hatem, they both have really done a very good jobs together with David to convince the committee of the Europa conference and the reviewers to really have this time a very great paper that fits nicely into Europa. So, of course, there's lots of things to tell about it, and we will hear about it from Tariq. But let me say it was remarkable in a couple of ways. Firstly, it is a very interesting application. Reverse time migration is something you use in oil and gas exploration. So first of all, it was really a good foundation of motivating the paper with a concrete application setting. Then, of course, we see that in the data domain, and I'm very pleased that this Best Paper Award really came out of my data analytics, data management, and machine learning session here as a kind of proposal to the whole committee. So this paper is really about the challenges that we face these times in memory. So the paper also talks about many terabytes that don't really quickly fit into memory, and you have to think about it. You have to have strategies around it. And that makes this paper also quite interesting, that given the timeliness of memory, non-volatile memory, and so forth, this is another interesting aspect why this paper then was contributed here to the conference as the best paper. And finally, before I take all the material away from Tariq, so that he doesn't need to speak or basically has his video to be played, let me say it was also the scalability in the end. So we have here really a paper that scales to massively amounts of GPUs across many, many nodes. And this is, of course, also what the Europa stands for, really parallelization, scalability to really a wide variety of nodes. And in this sense, I think I have talked a lot. Tariq will talk basically virtually inside the video, but is here also together with the whole team actually to answer your questions, I guess, after we play the recording. So I would say now it's time to play the recording. Congratulations again, of course, from all of us.
Hi, my name is Tariq Alturkestani, and today I'm going to present our paper, Maximizing our Bandwidth for Reverse Time Migration on Heterogeneous Large-Scale Systems. This research has been done in collaboration with Dr. Hatem Ltaief and Professor David Keyes from the Extreme Computing Research Center at the King Abdullah University of Science and Technology in Saudi Arabia. In our research, we implement a multi-level generalization of traditional two-level memory systems. One fast but small, the other large but slow, processing asynchronous prefetch and write back.
We had some technical problems. We will restart the streaming. Sorry.
Can accommodate more than 2 layers of memory and storage, and it dedicates a small number of available threads as I/O helpers. It also coordinates between levels of memory to minimize the size of buffers required. For a representative I/O-bound application, seismic inversion, we significantly outperform state-of-the-art provided solutions. on a Cray XC40 supercomputer, Shaheen 2 at KAUST, which is on the top 500 list, our proposed solution, MLBS, outperforms state-of-the-art parallel file systems as shown in a recently published paper. On the IBM-built Summit supercomputer, which is currently ranked number 2 on the top 500 list, using 2,048 compute nodes equipped with a total of 12,288 GPUs, MLBS achieves up to 1.4x performance speedup compared to the reference parallel file system-based implementation. MLBS is also demonstrated in cosmology, particle-in-cell combustion applications, and a classical out-of-core linear algebra kernel, Cholesky decomposition. In this talk, I'll define the problem, motivate our research, introduce our proposed solution and principal application, discuss some of the experimentations and the results, and I'll finally conclude with a summary and a future work statement. As we all know, there's a growing performance gap between processing units and storage systems. Asynchronous system calls do not hide the I/O overhead, mainly because of the limited buffer sizes. Blocking for I/O may amount for up to 95% of the entire wall time. We consider a major application driving supercomputer acquisitions. We could also see similar reports of more than 50% of wall time arise from climate and weather modeling applications. Iterative applications such as reverse time migration, write or read a huge amount of intermediate data at predetermined time steps. When a call to a write or read is invoked, the I/O library copies the data between the application space and the I/O library space. We have tracked the timeline for a seismic inversion application, and we have seen that the I/O library could sometimes be a bottleneck, causing the application to block, waiting for the data to be flushed from the I/O library to the storage system. New HPC systems are equipped with hierarchical storage. We have supercomputers that are equipped with the remote shared bus buffer, and we have supercomputers that are equipped with node local bus buffers. We have also supercomputers that host compute nodes that have access to GPUs with high bandwidth memory. Now, let's look at an application that computes on a GPU and outputs to disk a huge amount of intermediate data in a form of a snapshot. The computation will start from the GPU, and at a predetermined time steps, a checkpoint of the entire state or grid will be taken and it will be copied to the CPU. And from the CPU, it will be flushed to the parallel file system. This process will be repeated for the entire execution time of this given application. Now, this same application may require to read back all of these snapshots for further processing. The CPU would then prefetch these blocks or snapshots and load them to the GPU. And it will do so for the entire snapshots that have been dumped to disk. The goal of my research is to overlap I/O or compute through continuous pushing and pulling of all of the intermediate snapshots through and across all of the intermediate storage layers without stopping the computation. And in the case of reverse time migration, and as you see in this timeline, we want the computation and the I/O to be happening in parallel without affecting one another. Recently, we have proposed a multilayer buffer system, MLBS. MLBS utilizes all of the available memory and storage layers in a given system in order to overlap I/O and compute for the applications that use it. MLBS consists of two building blocks. One, a very simple set of APIs, write and read, and two, decentralized helper engines that help to prefetch and write back all of the data in all of the memory layers. The write API of MLBS copies the data in parallel from the application space to the MLBS space. Once the copy is done, then the application could continue computing while the MLBS helper engines move the data across all of the intermediate layers. The read call of MLBS is then as simple as a pointer swap. And the goal of the helper engines of MLBS are to order the storage and memory layers from fastest to slowest, to move the data between the application space and MLBS space, to conduct the actual write and read operations on memory and disks, to move the data between the layers, to cache in and out the data based on the data access patterns, and to ensure the separation of I/O and computation tasks. We have integrated MLBS into reverse time migration, vector particle in cell, hardware accelerated cosmology code, chaos adaptive reacting flows solver, general matrix multiplication, and Cholesky matrix decomposition. And in this paper, we're going to focus on reverse time migration. Reverse time migration, RTM, is preferred for modeling and imaging seismic data in areas of complex wave phenomena. Unlike one-way wave equation migration, RTM is the most advanced seismic imaging technique for decision support on drilling investments. The economic value of oil reserves that require RTM to be localized is in the order of tens of trillions of dollars. RTM requires fast computational power. Oil and gas companies, such as Saudi Aramco, Total, Eni, invest heavily into supercomputers. And significant portion of the time in RTM is spent in disk I/O. Therefore, our research has a direct impact on the P&Ls of these oil and gas companies. RTM requires combining at regular time steps a forward propagated source wave field with a back propagated receiver wave field. In the first phase, the 3D simulation states or snapshots of the source wave fields are computed and saved to disk at a predetermined time steps. In a second phase, the receiver wave field is computed and the imaging time steps along with the source snapshots are retrieved and correlated with the receiver snapshots to update the final image. We have experimented the scalability of MLBS and RTM on two powerful supercomputers, Summit and Shaheen. Summit is an IBM-built supercomputer with more than 4,000 compute nodes, where each compute node consists of 6 GPUs and a node local burst buffer. Shaheen, on the other hand, is a Cray-based supercomputer with more than 6,000 compute nodes and a remote shared burst buffer. Summit is ranked number 2 on top 500 most powerful supercomputers, and Shaheen is ranked number 45 on the same list. Our first experiment was done on Shaheen supercomputer. We used a CPU-based RTM code. We fixed the number of time steps to 3,000 time steps, and we fixed the grid size to 800 cubed per shot per node, and we've conducted an I/O at every 10 iterations. We measured write and read aggregated throughputs in gigabytes per second, and we increased the number of nodes from 1 all the way up to 2,048 nodes. The scales you see on the axes are on log scale. On the blue curve, you'll see the I/O performance as seen by the RTM app using Lustre file system. And on the dashed blue curve, you'll see the I/O performance as seen by the RTM app using MLBS. In the forward phase, the write phase, you'll notice that especially when we have a small number of nodes, MLBS can speed up the application or the write performance by almost 32 times. And as we increase the number of nodes, that speed up reduces to 3.5x when we have 2000 compute nodes. In the backward phase, you'll notice that MLBS was able to always prefetch the data and have it ready upon request whenever the RTM application needed it. Our second experiment was done on Summit supercomputer. This time we used a GPU-based RTM code. We fixed the number of time steps to 3000 time steps. We also fixed the grid size to 700 cubed per shot per GPU, and we've conducted an I/O at every 10 iterations. Remember, on Summit, every node consists of 6 GPUs. So when we have one node, that would mean that we would have 6 GPUs solving 6 independent shots. We've measured write and read throughputs in gigabytes per second, and we've increased the number of nodes from 1 all the way up to 2048 nodes, or 12,000 GPUs. On the blue curve, you'll see the I/O performance as seen by the RTM app when using the IBM parallel file system. The dashed blue curve shows the I/O performance as seen by the RTM app when using MLBS. On the right, or the forward propagation phase, you'll notice that MLBS can speed up the write operation by up to 3.8x, especially when using small number of nodes. The performance could be performance gain could be up to 1.4x when using 2000 compute nodes. However, on the read, the performance speed up of MLBS could be up to 1.9x when we have a very small number of nodes, and it could go all the way up to 18x speed up when we have a large number of compute nodes. Few things to note about Summit supercomputer. One is that the machine is equipped with a node local bus buffer, meaning that when an application is running on a node, only the application has access to that bus buffer. Therefore, the performance of the bus buffer does not really depend on the number of applications or number of nodes that are being used on the machine. Two, that writing to the bus buffer could bring you more I/O throughput, especially when we have more than 1000 compute nodes trying to write to the parallel file system. Three, reading from the bus buffer starts to make sense when we have 32 or more compute nodes trying to read from the parallel file system. MLBS's autotoner could see or measure the performance differences between the layers and could make a decision at 1000 compute node to change the order of the layers in order to increase the bandwidth for the application and to achieve up to 18x speed up on read. And finally, on Summit, we reduced the grid size to the point that all of the intermediate snapshots could actually fit in one GPU's high bandwidth memory. And as you could see on your left plot, we were able to have the application or the RTM instant work as if there was no I/O at all and achieve up to 3.27 wall time speed up. And then we increased the size of the grid a little bit to the point that some of the, or at least half of the grids, half of the intermediate snapshots had to be evicted from the GPU to the other layers, whether it's bus buffer or high bandwidth memory, and we were able to achieve up to 3.25x wall time speed up. And as you have seen, using a technique like this, where we utilize the high bandwidth memory as an intermediate storage layer, we could potentially speed up quite a lot of number of applications, especially now that the sizes or the capacity of high bandwidth memories for the new HPC systems or the new GPUs is increasing. And to summarize our contribution on this paper, we've extended our multi-layer buffer system that could continuously push the data up and down and across all the hierarchical storage systems to include the high bandwidth memory of GPUs. We've designed an online autotuner that could help MLBS to monitor and reorder different storage layers based on their sustained I/O bandwidth. We've evaluated MLBS's scalability on homogeneous system, Shaheen 2, and heterogeneous system, Summit, and we've used up to 2,048 compute nodes. We've also evaluated the benefit of using high bandwidth memory layer of MLBS as an independent layer and the only layer to store the intermediate snapshots of a small case of RTM. And finally, as a future work, and since we've seen that write and read operations could act very differently on different mediums or different layers, we are going to enable MLBS to have two different independent paths for write and for read. We are also going to integrate MLBS with more GPU-based out-of-core linear algebra routines, since they require a lot of movement of blocks between the GPU and the CPU. And we are going to enable a dynamic scheduler for the MLBS helpers to enable them to prefetch and to write back data based on the based on the online access patterns. With that, I would like to thank you, and I welcome any questions that you might have.
All right. Yeah, let me first thank you virtually for the interesting and very nice presentation again. The contact is given here. We have basically the end of the session, but I take it hopefully from the organizers that we get also 1 or 2, 3 minutes more for getting urgent questions. So if anyone has a question, please, now is the time to shoot. You have the possibility to put that either in the chat, or we have the Slack channel for this session. So please go ahead. So far as I see, there's no real question yet. So I would like to start then, while you maybe enter your question into the system, with one short question, which means obviously the topologies will vary in the future. And when you think about the data in motion, which you need for this, what are your plans to extend the MLBS for this to be more topology aware, perhaps?
Hi. First off, I'd like to thank you for awarding me this beautiful award. It's I also thank Hatem and Professor Keys for the efforts that they've given me, or for the effort and the huge pressure good pressure that they gave me to finish up my work. So regarding the question with the increasing topology and the increasing the number of layers in the future, one thing that I noticed in the research that not all layers can give you the same performance, and even the performances that they could give you are not always maintained at the same levels. So as seen, like in for example on Summit, we've seen, look at the beginning, when you have small number of nodes, using the bus buffer does not really make sense, but instead using the parallel file system is better. And as more nodes are, or as more nodes are basically write or use the bus buffer, the parallel file system, then a bus buffer becomes more active, or it could make more sense to your application. In the future, I think one of the future work that we would like to happen is to make sure that when we have an online a scheduler that could prefetch or cache the data, that it can know online where to put the data and to measure the sustained bandwidth for that layer. And if you use that, then you can have a perfect optimization of your system. So that's, I hope that answers your question.
Okay, yeah, very interesting. Thank you. So this is definitely an interesting approach to follow. Once again, to everyone here in the chat and participating in the Zoom, we have two options. Either you put your question in the chat, or you essentially use our Slack channel for questions.
So I see now a question from
excellent.
Paul.
Go ahead.
He's asking about the usability of MLBS in the cloud. So one of the building blocks of MLBS is this helper engine that prefetch and cache the data across the layers. So now the layers are all within like one ecosystem, which is a supercomputer. We could have another system or another topology where we have or another like setup where we use cloud resources for storing and prefetching and caching the data. There are especially in the database community, they use that topic is very hard to make sure that the latency or to access the data is reduced. At the moment, MLBS is not exposed to the cloud, but I think in the future we could expose MLBS as helpers to the cloud, to the different layers of the clouds, and we can make an online decision of where to put the data and what layer to use and where to prefetch and how to basically how to distribute your data across the cloud. But it's not been it has not been just right now. It's not done, but it's something that we should do.
Okay, excellent. Do you see the question of Rosa to finish off? I think with the question sessions here.
Okay, so increasing. Yes, I see. Yes, I see the question now. So she is asking. Rosa is asking about the. I think the slide where we show that there is an increase of the bandwidth for RTM when we jump from 1,000 to 2,000 compute nodes. So if we put the layers in a static way, assuming that we distribute, we say that our layers from the fastest to slowest are CPU, GPU, CPU, followed by like a burst buffer, and then a parallel file system. You would think that this is the regular, or this is what should give you the maximum bandwidth for the application. But we've noticed that we made sure that MLBS could actually, during the runtime, while it's running online, it could measure the sustained bandwidth for each layer and then make a decision to change the layer. So therefore, when we at the 1,000 compute nodes, MLBS decided that to flip the layers between the parallel file system and the burst buffer. So it used the burst buffer as the first layer, followed by the burst buffer, by the parallel file system, and that's why we saw that jump. And I hope that answers your questions, Professor Rosen.
Okay, so we have another question. I think you see that, but then I guess we also have to start slowly going over to the best artifact award. So I guess Tariq is also available via this email that you just see, further questions. But Tariq, if you could answer the last one now.
Okay, so the question is how can we know which layer to use or which layer to put the data first? What MLBS does at a periodic level or even at the initial step is to do a small IOR-like benchmark to the layer to make sure to measure the sustained bandwidth of that layer. And then it will create an order and say, okay, for instance, that we use now the parallel file system as a first layer, or we use the parse buffer as a first layer. So that decision is made through the helper. I hope that answers the question.
Okay, I'm sure it does. And again, I think thank you everyone also for attending this session. And of course, I guess, Tariq, you will be available or other collaborators from Chaos to ask or basically to answer more questions if questions are asked later. With respect to the timeline and so on, and because there's also later a session coming for data management, for data analytics and machine learning. So please feel free to stick on this channel because we have later a session after the best artifact award. So I think without further ado, I would go forward with this and ask the chair of the best artifact award to just take over.